Hello, this is Andrew with WMH Racing, and today I think we are going to look at a new motor. So there's a lot of hype on this motor, and I kind of wanted to pick one up and put it through the ropes on the Loadmaster, and also using the RPM Apprentice and see what we can come up with. So I wanted to do this on a brand new motor. So this video is going to be, I don't know, a little bit difficult, and probably quite long. So just, I don't know, I guess kind of bear with me on this, because I wanted to actually do, open the box, and then I'm going to have to take the motor apart, and then I'm going to have to measure all the different things. So I'm going to measure inductance with this meter. I'm going to measure the magnetic field with this meter. So this is one of my meters, right? I am going to measure the resistance with a milliohm meter. I believe that is the one that's listed in the Roar manual, that or Roar rules that they use. I'm going to measure some RPM values with my RPM Apprentice, and we're going to use the Loadmaster to put a load on the motor. Okay. So yeah, we'll see how this goes. Hopefully I don't mess up too much. Let's see. Let's figure out where to actually open this. Looking through the box, or looking through the camera, is always fun. Okay. I really am curious about this motor. I will say, I reached out and, I paid full retail for this. Told Team Powers, I said, hey, I'm a guy who builds stuff for motor testing. I'm not actually going to run this motor. But I'm just going to, test my products on it. And told them that, if they wanted to send me any other motors for review or put them on my videos, I would happily do so. But unfortunately, they only sent me the one. Which, I mean, I kind of figured that would be the case. But you get a completely unbiased review of this motor. Although I'm not sure how unbiased it is, because I'll be honest with you, I have never ran a 25.5 motor. All right, so let's see. What do we get in the box? Do we get a sensor cable in there? All right, we get a sensor cable. Nice short flat wire sensor cable. Awesome. It looks like there's maybe instruction manual in there. Yeah, I'm not worried about the instruction manual. I'm gonna put this sensor cable back in the foam box here. And this is our motor. I don't know. I mean, this definitely reminds me of the Surpass motors. Let's see if I have a V5. I have a Surpass V6. Okay, this reminds me of the Surpass V6 motors. Okay, Surpass V6, Team Powers V6. Now, I 100% understand that two motors can look alike, and they can be completely different. But these definitely share some design similarities as far as the aesthetics of the actual motor are concerned. Yeah, so we'll see. We'll see what it's got to show underneath the bonnet. All right, let's see here. We have 1 mil screws, 1.5 mil screws to hold the motor together. I need some music playing or something like that. The problem is copyright, right? So I want to listen to something because I hate the quiet. All I hear is the ringing in my ears. So, you know, loads of fun there. So if I keep rambling on, I'm sorry. We're going to use my motor assembly stand here, if I can put this stuff in with my left hand. All right, let's see. Pull this off. Yeah, it's even got the little locators and everything on the end belt. This really does look like a Surpass motor. I mean, I'm not saying it is. I'm just saying it looks like one, right? All right. Ooh, was there a... No, there was no shim in there. Okay, awesome. That's definitely a tight fit on that. Okay, yeah, I mean, I know that everybody says this is not a Surpass, but wow. Wow, does it look like one. Just wow. All right. So, all right, there's the stator. So first thing I'm gonna do, let's measure the field of the rotor. All right. So I'll put this on here. Wow. That is a very strong 25.5 rotor. Wow. Just like, yeah. All right. So I'm getting 1773 on the north side and roughly 1790 on the south side. Okay. So I'm pretty sure it used to be 25.5 motors had a smaller diameter rotor. So I know that's a lot stronger than the R1 25.5 I have, or the Trinity slot machine 2. So let's see. I said 1775 and 1790. So I'm just putting these in my spreadsheet. Just as an FYI. So yeah. All right, so now I'm going to measure, let's see, the next thing on my list is to measure the IR, the stator IR. Okay. So I'm going to use the Instec GOM 804 meter to measure the stator IR. All right, so I'm going to go and measure. I'm going to go ahead and measure, whoops, two tabs. So I was thinking that at first I would just do it one, but I think most of the time when you guys do this, you're actually measuring two tabs. So I'm just going to do from one tab to the other, which essentially is double the IR, right? All right, so I have 79.77, so 79.8 for AB, 79.8 BC. I have, I'll go 79.5, and AC I have 79.6. Let's look at AB again, see if it got any closer, you know, because 79.8 compared to those was, yeah, but it is 79.8. All right. So that is the IR measurement. So now I'm going to measure the inductance with the DE5000. So this is an LCR meter, and this will also measure the DC IR of the stator. It's not going to be as close as the GOM 804, right? I think these things are, I don't know, 70, 80 bucks or something like that. They're not that expensive. You can get these on Amazon. So yeah, again, they're not that expensive, but I'm going to go ahead and measure the internal resistance. I'm going to measure the resistance using this LCR meter and see how close we actually get to the values of the GOM. It does not have the same resolution. So bear with me. Capacitance, resistance. It does not like me. Oh, DC resistance. There we go. Maybe. Okay. Is there something wrong with the... Well, you know, if you got it plugged in backwards, it ain't gonna work. Oops. Ah, that's fun. Learn to use your equipment, Andrew. Okay, let's do this again. DC resistance. Okay. All right, so we're showing, like I said, the resolution is not quite as good, so you're not going to get that third digit. So it's showing 80 milliohms, which is, you know, the 70, I can't even remember what it is now. I have to go back and look at my sheet. The 79.8 milliohms rounded up. So, well, I mean, you know, all right. I was thinking this would actually work pretty well, but I guess it's not. So it's only going to show down to that. Yeah, it needs one more digit of resolution for that. All right, so never mind. We'll go back to the inductance then. All right, so the inductance, I do want to measure one phase. So I'm going to put that right there, and I'm going to put this right there. Okay, and we have 74.8 microhenry. Sorry, I'm trying to do this on my sheet, on my Excel sheet at the same time, so this is a little bit difficult. So 74.8. 75 microhenry. And what is the last one? $75.2. All right, so they're all really close. Now, I have been asked before, because should you measure inductance with the rotor in? And the answer is no. If you're going to measure the inductance and keep track of the inductance of your motors, do not do it with the rotor in the can. The rotor will add, it will add its own magnetic field, and it will mess up the inductance reading. Okay, so now I am done with this. I'm gonna set this over here to the side because it's, you know, a massive thing to be in the way, right? I am going to bring the RPM apprentice in view. Okay, so I need to plug this in. Maybe, you know, plug it into the right spot. Again, learn how to use your own equipment. Okay. And then I'm going to plug this into the slave motor, since that's where I'm going to be measuring the RPM. All right, awesome. Let's see here if I can get a little bit closer. All right, so I'm going to put the motor back together. Now, these are kind of the only two things I'm worried about now. I can turn this off. Kind of move this out of my way. All right, put the motor back together. I'm not sure why I did all that. All right, let's see. This black thing's got to go in there and locate the screws correctly. That's kind of annoying. Sorry, I'm doing this off camera. It's a little bit difficult. There I go. No silent, or no, not no silence. There I go with the silence because I'm concentrating. Yeah. All right, so I have heard that this motor may like lower timing than what we're used to. So I'm gonna go ahead and set it at 30 to start. Where does it come from the factory? 10, 20, 30. Oh, how about that? It comes from the factory. It comes from Team Powers, set at 30 degrees. All right. So, put this here. All right, since I am only worried about loaded RPM, I am not... Oh, let me think about that. I guess I should actually run this in series. Sorry. I'm going to run this in series with the tunalizer. I don't know why I want to do this. I have this right here. All right, so this will go from... Oh, wait a minute. This will go from the tunalizer into here. And then from here, it'll go in... Maybe. Oh, well, that's just annoying. Got one of those. Okay. All right. Let's see here. All right, so we'll do an auto. So we are using the standard 1 ohm resistor bank for this. Move this out of the way, that out of the way. What do we got here? We got this and this. All right. First things first, I'm going to set the RPM, time to target RPM to, let's do 10,000 RPM. And 2 will be 7,500. One will be 5,000. Okay, awesome. All right, timer. We'll reset this, and we'll do the auto test. Everything plugged in. Give it a go. Oh wow, so there's a max RPM of 16,726. We might change these values. So let me hook it up to a load and see how many RPMs we're spinning under load. Problem is, you gotta kind of guess. And so as the timing goes up, we'll get more and more RPM. All right. So we got 14,000. So I'll go ahead and change these. Let's see. I want to get this pretty close, right? So we'll make T2 10,000 RPMs. And 5,000 still seems fine. So yeah, that'll work. Okay, settings, timer, reset. Okay. All right. Now let's Let's try this again. Okay. Alright, so on my spreadsheet we're doing 30 degrees. We have an analyzer timing of 29.5 is my average. Looking at the we got basically 29 degrees, 29 degrees, and 31 degrees. Those aren't completely too bad, I guess. 2205 kV. And time to RPM. I just have 10,000 on my spreadsheet, but I'm going to use, oh, damn it. Sorry. Looks like I did 13,000 instead of 14,000. I swear to God, we're going to get this right one of these days. All right, 596. All right, so 596, let's see, 1.32 amps. Okay, there we go. Now, let's put a load on it. Okay. Sorry, I gotta run it again. Forgot to reset. Okay. Do it again. So you kind of, one of the things I want people to pay attention to, now I guess you don't really have to, but if you listen to the pitch of the motor going through the 3 different cycles, so the first one it goes through, it just runs the motor at full throttle, then it kind of runs a little bit of reverse, and then the third one, when it runs again, it's actually running in sensorless mode. And so that is where the tunalizer is actually measuring the timing advance on the motor. It is doing it in the sensorless configuration. One of these days, I'm going to hook this up to my scope and show you guys the signals, what the signals actually look like in the different modes, and why Hobbywing uses the sensorless setting to measure the timing. It's much easier. The signal's a lot cleaner to look at than when you're actually using when you're doing the standard run and basing it off the sensors. So anyway, yeah, I will do that one day. I'm not sure exactly when that's going to happen, but it'll be fun. Wow. Under load, this dropped to 21.9 degrees timing. So we could go into that as well, but I don't really want to go into that right now. All right, so 21.9 degrees. Basically what's happening there is the flux inside. The magnetic field kind of distorts inside the can as you're running it. And because the magnetic field distorts, it changes when the Hall effect sensor senses the rotor position crossing the north to south pole of the Hall effect sensor crossing that. And it, like I said, it's changed because the magnetic field changes inside the cam when you're running the motor. But that's a really big number right there. They're usually only a couple degrees off. So yeah, wow, that's kind of crazy. All right, so amp draw 7.7. All right, so now we'll go to the next timing mark, which will be great fun, right? And I'm not even sure what that is. Probably gonna have to put my readers on to read the timing marks here, because old people don't have good eyes. All right. It looks like this thing has timing marks in 2-degree increments. And my readers might not be enough. I might Need like a magnifying glass. That's just too funny. All right. Woohoo! That is a very, very snug into the Loadmaster there. Okay. I'm going to go ahead and reset this. So, what was our last 596 milliseconds to 14,000 RPM the last time? Awesome. We expect this to be faster. 578 milliseconds. All right, awesome. 578. And we have 1.25 amps. We are now drawing less amps than originally. With our M-bell timing went to 28. Did I go the wrong way? That's gonna be embarrassing, isn't it? Absolutely, I did. Awesome. Oh my God. Well, you know, live videos, no one takes, right? Well, I guess not live, but I wanted to show this as a brand new motor. Maybe I'll block that part out. I don't know. I hate editing videos. All right, we're going up to 32 degrees this time. Sweet. All right, we have more time. I still got going to 13,000 RPMs. I thought I changed it to 14,000. Well, we are doing to 13,000 RPMs because I thought I changed it and I didn't. Anyway, 605 milliseconds. Let's see, 31.3. Oops. We have 2223 kV, 2223. Okay, now let's go ahead and hook this up to a load. Yeah, since 13,000. All right. So it still sounds like it's got more timing in the sensorless version than it does in the sensored. And if we actually look at these, you can actually see that M-bell timing is at 24.2 degrees, where in sensorless, it's automatically going to add, it will be 30 degrees timing built into the controller. So that last, the last run being in sensorless is sounding a little bit strong, or a little bit faster because of that. So anyway, let's see, 24.2. We got 1888. We went up and up in the amount of time it took to get to 13,000 RPMs. All right, so now I will go ahead and increase the timing by 2 degrees. I swear to God, I'm going to increase the timing this time. How far we actually want to go with this. I'm definitely thinking that we're going to hit at least 40 degrees on this, because we're definitely going to want to be at least 30 degrees of timing with the with all the all the fun stuff happening in the can. So yeah, I'm thinking we'll want to be timed to at least 40, which is a little bit different than what people are saying. I'm hearing like mid 30s for timing on this, so I'm not buying it right now, but we'll see. See, that was, oh, wait a minute. So there's a difference between loaded and unloaded, right? So loaded or unloaded, you're definitely getting past 30 degrees. We can hear it right there. So 34. Let's see, KV is 2271. Our time to 13,000 RPMs of 608 milliseconds is pretty much the exact same as it was on the previous run. A little bit more current running through at that time. All right, great. Now we'll do the loaded. But first I want, no, you know what? Well, yeah. So I'm going to run this again and just pay attention to the pitch of the motor. Nice and high. And that last one was definitely a lower pitch. So it's not spinning as much. We can actually look at the, I don't know why I did that. We can actually look at the live RPM over here. 17.2 and 15.5. So yeah, we're definitely over that. But when we do this, seeing where the actual timing is, or where it is, so loaded. All right, reset this. There's a 14.5. Hey, all right. So we're over it now. At 27.4 degrees is what it's reading. 27.4. Okay. Let's see, we got 1923 RPM. That's a good jump from previous. Time to target is 831 milliseconds. See, our time to target RPM dropped too. That's good. 8.31 amps. Okay. Now we'll go ahead to 36 degrees. It's kind of like looking at my graphs right now. All right, so anyway. I know. Long videos are boring. I know, trust me. If it's any consolation, it's late and I should be in bed. So long videos are boring for me too. Especially because I have class tomorrow, which is awful. These are not, let's see, 32, 30, let's say 2. How many ticks? All right, so 30, 2, 4, 6, 8. Okay, let's go down to, says these are very hard to see. There we go. So, for those who don't know, I started doing this because I broke a tool. It's really kind of funny. You guys are familiar with one of the other rotor checkers on the market, right? Now, anyway, I broke one. I hooked up my 24-volt power supply to my soldering iron, one of those like T100 soldering irons, which I can't stand and I don't use anymore. But a lot of people like them, so you know it's fine. But I hooked up one of those, and it smoked the voltage, the onboard voltage regulator of the rotor checker. All right. So I reached out to the company. I said, "Hey, I messed up your rotor checker. Is it possible that I can send this somewhere to get it fixed? I'd be 100% happy to pay for it. And they never replied to me. Oh, how rude, right? So I decided I would... I figured, how hard could it be to build one of those, right? Actually, that's not true. First thing I did is I took it apart and went, oh yeah, there's just a bunch of stuff in here. I can figure out what this is. I mean, hell, everybody took an electronics class when they were in junior high, right? And can do this. And so I did. I opened it up and I completely destroyed it because I didn't know anything, right? And I'd never soldered on a small circuit board like that before. I destroyed some traces and everything like that. And then I went online and I started searching pretty much how to build my own. And so I did. I built my own. And that was the Rotormaster V1, the original V1 version, right? And I open sourced that and I put plans out online for people to get if they wanted to. But let's see, we have 831 milliseconds again, 28.5, sorry. But I still had people reach out to me and want me to build it, even though I said, well, here's all your... This is... Oh, man, yeah, I'm talking and doing this. I think I messed up here. I think I have 36 degrees at 34 and 36 degrees. That's perfect, right? Oh, that's what happens when you get talking. All right. Well, this is definitely 36 degrees. I'm going to go redo 34 degrees. So yeah. Anyway, I did a lot of searching to actually build that first Rotormaster, and my intention really was not to start a business out of this. My intention was to build that and tell other people, hey, this is how you do it. But yeah, anyway, there's a lot of things that I found out really quickly that I should do different on that. So I did. And so anyway, that first year, probably a first year, was a really, really big learning curve. I spent most of that year learning how to do 3D CAD programs so I could 3D print stuff, because, I'd never opened up a CAD program before. So yeah, lots of craziness. Let's see, this is 606. And I don't know. It was quite a bit of fun learning all this stuff. And then time went on, and I got some other projects to do. Well, I mean, I designed this Loadmaster, the first Loadmaster. It was, to be honest, it wasn't a revolutionary design or anything. There's plenty of companies out there that have made, loaded motor tests before. It was just a matter of putting it all together in a way that it was useful, and run off all kind of, a tunalizer. Trying to make this as easy as possible, right? So anyway, after designing the battery wizard, which took me 5 months, at about 25 to 30 hours a week. So I was working full time at that point in time, as a network engineer for a medical company out of Chicago. So I was working, 45, 50, sometimes 60 hours a week at work. And then I'd come home and do design on the Rotormaster, or not Rotormaster, sorry, the battery wizard. So another 25, 30 hours a week for 5 months. Now, it took me 5 months to design it because, well, I was learning. I mean, honestly, I was learning because I didn't know any of this stuff. So I had to learn. So I had to learn how to code. I learned how to do all sorts of crazy stuff for that one. And let me tell you, it was fun, but it was difficult as well. So anyway, I'm sorry, I'm typing in numbers in the Excel graph up here. Bear with me. It was right after I released that that I decided that I would actually go back to school. So prior to the designing that, I had an associate's degree in physics. An associate's degree in an associate's degree in physics. All that really means is that I took a couple of math classes and I took calculus-based physics. It doesn't mean much more besides that. Just as an FYI, it's not really that big of a deal to get an associate's in physics. So anyway, we are going to go to 38 degrees now. Now, though, back in school, you know, the funny thing is, like, I think it was like a 16 year span from the time I got my associate's degree until I went back to school. So back when I got my associate's degree, I took Calc 1, I took Calc 2. And, you know, I did pretty well in those classes, right? And I took calculus-based physics. But I come back to school, and I'd start taking Calculus 3 after not taking a calculus class in, 15, 16 years is a little bit eye-opening and very difficult. So again, I did well though, so it's all right. So I started off 9 credit hours. So just to let you guys know, when I started school, I was still working full time as a network engineer. So working 50 hours a week as a network engineer, taking 9 credit hours. The classes I took were Calculus 3 and 2 engineering courses that were required for what engineering transfer students, which was technically what I was, because I had an associate's degree and I was going in. So I was an engineering transfer student. And I have to reset this and try this again. Okay, sorry. One of the classes, though, was a basic electronics course. So that was one of the engineering transfer courses. It was, honestly, it was a basic electronics course and basic coding, which I had taught myself already. So I was I was definitely good to go on that. In that class, I think I missed one question on one exam and got full points on everything else. So that was really fun. That was an ego boost, where my Calc 3 class was definitely an ego demoralizer. So but anyway, like I said, I still did pretty well. Even in Calc 3, I still did well. So the next semester, I dropped down to 7 credit hours, took a C++ course and a communications course, and did really well in both those courses, and less time was good. And now I'm on my 3rd semester back to school, taking Physics 2, which is basically electromagnetism. I'm taking a physics lab, which is horse manure. I'm sorry, I said that out loud. Yeah, it's not a very good lab. 100%. It's kind of awful. And then I'm taking DC circuits. Needless to say, I'm doing really well in DC circuits. The physics lab, I'm doing completely fine in and hate it. And physics 2 E&M, I'm doing really well in as well. So, yeah, next semester though. Next semester is actually when it gets hard. Next semester is differential equations, AC circuits, and digital logic. So, yeah, it's something to look forward to, right? Let's see. So far, our graphs are kind of not really doing much. We're at 38 degrees. I'm going to go to 40. And I've run out of stuff to talk about, too. So I've thought about doing some YouTube videos on what it's like to go back to school at 50. I go to a state university. Actually, I go to the University of Kentucky. So anyway, and there's just a bunch of kids there. Like, I kid you not, it's a bunch of kids, and I feel completely out of my comfort zone going to school with people that are my kids' age, right? I'm like, I'm old enough to be their dads. And I'll have more in common with the instructors, I think. I'm even older than some of the instructors. It's kind of nice. Maybe some of the instructors I'm not older than. But, yeah, they don't really want to talk to me because, I'm a student. So I get to interact with, a bunch of 20-year-olds, which is, it's interesting. It's just a whole different dynamic. But for the most part, everything seems all right. 621 milliseconds and 2.25 amps. I don't know. I'm really sitting here trying to do this video, trying to come up with something to actually talk about, and I've like done a lot of rambling on, and I probably made a lot of people tune out of the video already because of it. Especially since I'm talking and messing up at the same time, right? And of course, I didn't hit the reset button there, so we'll do it again. All right, so we are staying right around the same time to target RPMs with every single one of these passes. So that is something. Mostly the time to target RPM is kind of comparing one motor to another motor. So you can see how long, how fast the acceleration is for one motor versus another motor. So I will tell you right now, 40 degrees kind of looks the best out of all these other ones, and that's just based on kV increases. We started out with a kind of a good boost, and then we had a massive boost at 34 degrees, and then kind of nothing at 36 and a little bit at 38. And then now we had another good boost at 40 degrees. So far, numbers are still kind of like, they're just kind of like hanging on in there. Not doing anything spectacular at this point. Right now I see no reason to time it below 30 degrees at least, or sorry, below 40 degrees at least. How far we actually want to go. I was kind of hoping we'd be able to stop at like 40, but we're gonna keep going. Maybe the motor comes alive at 44. I don't know. I have no idea. Gotta hit the reset button. Keep forgetting it. All right, we'll do that again. Well, see, that was 645 milliseconds. So now we're taking more time to get there. But that was a lot of RPM, though. 40.8. 2334. We have a small boost in RPM. 2.47 amps. Okay. I've run out of stuff to talk about. Went through my whole life story there. Anyway. Yeah, so in case you didn't realize it, the degree that I'm trying to pursue is electrical engineering. And it is completely eye-opening. The amount of things that you learn that you didn't know. Like, I swear to God, the more that was a good boost from 42 degrees. And loaded, we had a better time to 13,000 RPM. So, I'm not seeing this. We're still gonna go up in timing. I don't see, like, this motor is starting to come alive now. I mean, and it was almost our best percent kV maintained under load there. I mean, we've been running right around 84 to 85%, and it actually came up a little bit right there. Yeah, I'm not convinced that the 25.5 should be ran at lower timing. So, all right, up to 44. Maybe people are just over gearing them. Anyway, all right. Yeah, you can hear it screaming, and of course I forgot to hit the reset again. Oh my God. It's so awful. You know, this would be really awesome if it tied into the tunalizer and then I didn't have to worry about it, right? But that's not the way it works. All right. Ain't much I can do about that. I can't directly access the tunalizer and say, hey, start at this time. So that is kind of one of the things, though, with the RPM Apprentice. Like, because I can't, you can't time it exactly right. So the Hall sensors, there's 3 Hall sensors in the motors. Everybody knows that, right? They're latching Hall effect sensors, so they pick up on the north-south pole, and when it flips over, it it basically sends the so that was a really big kV increase. Wow. It basically sends a signal, a high signal or a low signal, depending on if it's reading high or low on the poles. And basically what I do in order to measure that, the motor can rotate up to 60 degrees before the RPM Apprentice could effectively start. So basically, I set an interrupt for the first rising edge on one of the Hall sensors. So those Hall sensors are, well, they're 120 degrees apart, but you're reading you're reading basically 2 edges per, or 2 signals per sensor, because it's only a 2-pole rotor. And it will, so basically that evens out to, or it runs out to 60 degrees, sorry. I don't believe that time. Wow. Wow. We're going to do that again. Wow, that is a massive difference. 2148. That is 172 kV increase from 42 to 44 degrees of timing. And the current even went down. What? And now we're at... What is going on here? How is that like... All right, so this motor just like came alive at the 44 degree mark on the can. 40.7 inside the can and loaded. Make sure I am 44 on the can. And it just came alive. I mean, just the graph on this looks like crazy. If somebody said, hey man, make sense of this graph, I'd say I can't make sense of that graph because it doesn't, like, something's wrong with your data. You did bad testing. Wow. Okay. Anyway, let's I don't know. This backed up. This doesn't seem like unloaded. It still seems like it has been. 46.1. 23.95. 3.39. Wow, this is this motor is definitely confusing me. I would say let's reset this. We're back to 799 milliseconds. So it went back up and the kV is 2000. I swear to God. What is the deal? 2003. And what's really messed up is even though I went up in timing, the internal timing still measures approximately the same. What happened? Oh, this has got me so confused. Now, I'm gonna go reset the motor. I'm gonna go back to that 44 degree mark on the can and see if I can get that magic back. Like, where did that go? That is insane. I've never seen a motor do this before. Ever. So I'm going to go back to this 44 mark. And see if it produces the craziness again. Because I don't really understand that. I'm just going to run the loaded test. Yep. Back to 700 milliseconds. And a kV of 2151. All right, so I'm not even gonna go beyond this. I guess I have to, right? So I want to show you guys because this is baffling. Kind of see what we're looking at here, and you see that our kV, kind of, you know, goes along this nice little thing, right? kV, so 1877, 1888, 1920, 1923, 31. So, you know, you're increasing, and this is the under load, by the way. And you keep increasing, keep increasing. And we go from 42 to 44, and it goes ballistic. Like, I have never seen a motor do this. Never seen a motor with a kV jump that big under load, like just completely out of, like, this is one of those points that you can't, I don't even know how this is possible. All right. Anyway, then the next time you mark that kV drops again, I realize I'm not making very much sense while I'm speaking with this one. Yeah, this does not follow. If we were to plot all this, right, this does not follow, right? There's no way you could interpolate this from the rest of the graph. This is just insane, completely insane. And then I went back, because if we hit this mark, and I thought, well, maybe it's a goof. And then I went back to the 44 again, and yeah, so I'm not sure. I want to see more motors and see if any more of these motors has some like magic value in them, because that's almost like what that seems like, a magic value. It doesn't make any sense to me. None. Okay. Yeah, so I'm going to I am going to go up to 40. Let's see, I did 46. I'm going to go up to 48 and see what happens at 48. Maybe 46 just didn't like me, right? So I'm going to go up to 48. All right, so we're at 44, 46. Go up to 48. Okay. And the other thing to notice, and I'll show you when I go back and do this. Yeah, see the RPM spinning like crazy. We definitely won't want 48. Hearing the RPM shoot up like that makes me think we actually got no more RPM than the 46 mark. Oh, sorry. Let's try it again. And 627 milliseconds. Okay, and still 23. Yeah, and 3.56. Okay, now we'll do loaded. I'm hoping this will be the last mark here. Okay, go back to that one more time. Reset. Back to 784. Yeah, this is not... I'm not sure. And 41.1 degrees inside the cam while everything's happening. 2018. Yeah, I don't understand. I am going to one more time lower the timing of this, because I just pulled this out. Let's see if we can zoom in on there. So right around 48 degrees. That might be like 47 and a half, right? All right, I'm gonna go back. I'm gonna go down to 44 degrees. If my eyes can do it. Back to 44. Screw this in. Okay. A little bit under 44. All right. It's like 43 and a half, 43, I don't know. And I'm just going to do the loaded test. All right. And here was our last one, 10.55. That was at 48 degrees, 10.55. Current KV was 2018, right? 784 milliseconds. All right, let's see if we can hit the magic again. Nope, that's not the right one. I lost it. Timing is slightly not the right one. All right. We had to find this spot, because the spot I don't even know what to do. 100% don't know what to do here. Let's see. It said 40.7. This thread's 36.4. This motor is, maybe this motor is just bad. That's possible. It's possible this motor is just bad. Maybe I got like one reading on it where it was, good motor. I don't know. Oh, yeah. That was unloaded. I need the loaded. La, da, 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 da. There we go. Found it. $713 milliseconds that time, 2147 kV. That matches back to what I had up here. And for some reason, this motor, I cannot tell you why, but there is a spot on my motor. Now, I have no idea. This is a brand new motor in the package. The inductance looked fine. IR looked fine. I cannot explain why this motor is doing that right there at this 44 degree mark. It was hard to find. To be honest, I think I probably stumbled on this by accident almost, because you saw I just touched the timing just a little bit. Because yeah. So here, I'll show you what I ended up on the can. I'll pull it right out of here and show you. From that last one, right? That was like 40, I don't know, 43.5 or whatever. All right, there we go. 44. .2, I don't know. 44.5, right? So yeah. A motor just it just came alive right there. I've never seen a motor do that before in my life. Not to that extent. That's now I'm really curious if I got a bad motor, or if this motor is, I don't even know. I just don't know. Like, yeah, I can't explain this. All right, anyway, I'm going to finish this video by trying to pull the phone back up and go onto the screen and at least look at what we did again. Yeah, I don't know. I'm a little bit stupid. All right, so roughly 80 milliohm resistance on each of the phases, roughly 75 microhenries on the inductance. The rotor is pretty strong. I'm 100% timing this motor at 44 degrees is what I called it on the can. We had a really good, I just don't understand this. I really don't. I mean, we look at these time to target, this was 13,000 RPMs, mind you, 13,000 RPMs. So we look at these time to 13,000 RPMs, we're right around 830. Then we drop down a little bit around 800, and then we hit that magic timing mark, which were in 700 milliseconds. So a tenth of a second faster, a huge, massive increase in kV. And if we look over here on the loaded or unloaded side, we don't see the same things happening. We have a 37. This just doesn't make any sense to me. 37 more RPM. Or sorry, not RPM. 37 kV increase on the unloaded version and 172 on the loaded. Okay. Well, I have no words. The graphs look absolutely insane. I forgot to get the current draw on the... Oop, dog. Bless it. I forgot to get the current draws on these. They went back up. I remember that. They went back up. It was 10... This was like 10 amps, right? On the 46, I'll probably go back in the video and find it for sure, but it was definitely over that. So... Yeah... I've got nothing. I know. Honestly, I don't know, and I want to know, and I realize that I'm saying I don't know a lot, and you know, on a video, and I really want to redo this video because it's awful, but I'm not going to, because you guys watched me open this out of the package. So yeah, if you guys got an idea of why, go ahead and put it in the comments, why. But anyway, so yeah, this is Team Powers 25.5 stock spec V6S. All right. Thank you.